Oh my gosh, thank you. Yeah, that vending machine is always taking people's snacks and money.
Every time I get, it's always the Cheez-Its and these that get stuck. And unfortunately, those are my two favorite things.
Yeah, last week they like left the vending machine kind of open.
I would have taken advantage of it. I got all my snacks that I lost back.
I know, we did the good thing and just like sealed it back up. Because initially I was noticing that there were two like sun chips stuck in there, so I was like, damn, some poor person got really screwed. And then when the janitor and I were playing with it, we're like, shit, this whole thing's just. And then he told me a story where I guess in college back in his day, they forgot to lock it back up and they just stole everything and had a party.
Ask you again on this.
Oh, of course.
So, I thought I had it, but how do we actually determine the equilibrium?
So then,
It's associated with the absorbance, is that right?
yeah, so you have to make an Excel graph.
Okay, so you make an Excel of part A?
Yeah.
Okay, and that'll give you the equilibrium.
Yeah, we'll give you the relationship. I could do this and email it to you. I think we have plenty of time.
Okay.
Yeah. But yeah, so then you'd plot your concentration. So 4 big E. So that's the same thing, the E.
Okay.
And then 8 E, -5.2 E. And plot 0. Oops. And then just make sure it's always like an X, Y, whatever. Oh, come on. Chart. Come on. I swear I typed this in earlier when we were doing it.
I know.
All charts. X, Y, there we go. Driving me nuts here. There we go. That looks like a great line, actually. So yeah, same thing. So now you have your equation.
Oh, okay.
And then now you can back calculate, well, the absorbance is that. And then you'll have to adjust. So yeah, like, oh, you already did that.
Yeah.
Perfect.
Okay.
And then you'll just plug it in with the Y value, solve for X
Oh,
to get
okay.
your molarity.
So the, let's see. So with that equation, I'm sorry.
Yeah, because this is your Y value
Okay,
absorbance.
so plug this in for Y, solve for X.
Yeah.
Okay.
quick. You can open Excel, right?
Yeah.
Oh, let me just reply to you. Oh my gosh. There it is. Okay.
Perfect. Thank you.
Yep, no
All right.
problem. Yeah, your calibration points were so nice. I'm just looking at the R squared, like 0.9973. I was like, nice.
Did something right.
Yeah, I mean, that's always a good start, especially with, it was scaring me when everyone was getting negative values for the next part. What is going on?
Okay, so there's 2 of the labs.
Perfect. I know, and just like I need to tape y'all down to finish the work, I think I need to tape myself down. Like yesterday, I didn't do much grading. I don't know. I just like was running to different meetings, and you know how it goes. Like.
Doesn't the reactant go on, or the product go on top and then the reactants multiply on the bottom?
Yeah.
So would that one be correct? Because it has to be squared because there's two in front of them.
Yeah.
And then the O is just not squared or anything because there's only one O.
Correct.
Okay, thank you.
All right, I guess we'll get started. We seem to be missing a lot of your class today. There people are. All right, so let's just go over end of the year plan again. So don't forget, today's the last day for the lab final. So that should be mainly my Thursday lab people or anyone else that needs to make up the lab final. So that is your chance. So take it, take it, take it. And like I said, it's just weighted the same as a lab. And then, so also we have on the docket, so of course we'll take our quiz today over chapter 19. But then up at the front, I have chapter 20 quiz, and Dorothy and I have decided that we're gonna do chapter 20 quiz as kind of like a bonus take-home quiz. So take it home. You know, if you give it back to me, it can replace one of your other quizzes, so I'll end up dropping like 2 or 3 quizzes total. If you don't take it, it doesn't matter, and it won't count against you. So take advantage of that if you want. So don't forget to grab it. The homework is also there. I apologize for not handing it out on Tuesday. We just never got to chapter 20. And then also today's the day for makeup labs. So I haven't gotten any emails, but it still bug me last minute for makeup labs. So make sure you have everything complete that you need to do all the calculations at home. And then so that brings us, so next Tuesday we'll review. And then we'll have our study work session probably after, so in case you need to turn stuff in, so use that time, collaborate. I'll be here, of course, answering questions if you need. So just get everything finished up, and then that brings us to Thursday, where we'll take our final. And of course, don't forget your paper. So I think those are due. People said the 17th. I forgot. What? 14th. See? You guys are on top of stuff. So do the 14th. So get those in so I can grade them and all that good stuff. Right. Any questions?
So you said you wanted paper copies of the paper, right?
Yeah, I prefer paper copies because I'm kind of old-fashioned and will want to write and squiggle things. Other questions? If you absolutely can't hand it to me in person, I'll take email. I don't think I opened up a Blackboard spot. But I prefer email over Blackboard just so I can like print it, again, like an old lady. Other questions?
And you said that was supposed to be in ACS format?
Yeah. So ACS for the citations. And again, if you don't get it perfect, that's fine. Like, try to do it in ACS, and that's part of why we're doing this rough draft and corrections, so that we can learn how to properly cite and all those good things. Other questions, comments? All right, let's get into acids and bases then. And so let's just start with our general property of acids. And you might know this from, of course, eating acidic fruits or something. So they have a sour taste, so I'm sure you have eaten lemons before. Those are pretty sour. They also have this ability to dissolve metals. We've probably seen that in lab with like hydrochloric acid or nitric acid dissolving those different materials like magnesium. They also have the ability to neutralize bases. So you've also kind of seen that in lab, like that's why we have the spill kits with the citric acid powder. So that's, of course, your base neutralizer. And again, citric acid is used in like candy making, so that helps give that candy like a sour taste for gummies, stuff like that, or Sour Patch Kids. And then for litmus paper, so that it changes blue litmus paper to red. And of course, some examples here. We have hydrochloric acid, very simple acid, or something like an organic acid, shown here, acetic acid, where this is our acidic proton. And so now here's just a table of kind of common acids. And so y'all are pretty familiar with hydrochloric acid, I think, at this point. And this could also be used in like metal cleaning. It's used in a lot of like ore refining, or it's also your primary component of your stomach acid. And then there's sulfuric acid, so that's used in like automobile batteries. It can also be used in like fertilizer manufacturing, electroplating of copper. Nitric acids, we've used some nitric acid in lab, but that's also key in like fertilizers and explosives. That's pretty good use of nitric acid. Acetic acid, so who knows what acetic acid is again? Vinegar. So it is vinegar. Obviously the vinegar, your household vinegar, is very, very dilute acetic acid. And it can also be used in food preservation, of course, and different sorts of manufacturing. So citric acid, so we mentioned, so that's used in like candy making, but it's also, of course, the acid that's found in lemons and limes. It's also used to adjust the pH in like foods and beverages. You often see like citric acid as part of your foods and drink. So carbonic acid, this is just in our carbonated beverage due to the reaction of carbon dioxide and water. There's also going to be a small amount of equilibrium in the sea, so you can think about that. So it's all a one big carbon cycle. So if you have more CO2 in the atmosphere, then more can become dissolved in the ocean and kind of go back and forth as well. Then hydrofluoric acid, so this is super useful in metal cleaning, and then glass frosting and etching, so that's used a lot in like silicon chip manufacturing and clean rooms, so all that. I generally don't work with hydrofluoric acid though. And then so phosphoric acid, this is also used in fertilizer. It's a biological buffer. And then also beverage preservation, so you'll see phosphoric acid in like soda as well. And so if we compare, so now let's look at what organic acids are. So organic acids are anything that have this carboxylic acid, and that's this group. So if we draw that out, so that's C with a double bond O, and this OH, and so this is connected to whatever else. And so the important part to kind of understand is why this is an acidic group and why this proton in particular we call the acidic proton. And so we can do that. So if we deprotonate it, so just plucking off our hydrogen here, so that gives us our deprotonated form. And then again, why carboxylic acids, why they make acids, why it's appropriate, is because its negative charge is resonance stabilized. So we can draw our resonance structure, so we can move those electrons here, move this double bond up to that oxygen. So now we'll draw this structure. And again, all that's essentially saying is if it can go back and forth between this oxygen and our other oxygen, right, is it's resonance stabilized across all of this. So sometimes you see it kind of abbreviated like this, where it has these kind of half bonds here, and then some sort of negative charge, again showing that this negative is all along here, delocalized, so that really stabilizes it and makes it, again, favorable to lose that proton. So now looking at bases. So bases, I don't know how often you guys have tasted bases, but they taste bitter, so they're unpleasant. I don't know if anyone has had their mouth washed out with soap or if that's too old. But yeah, you generally don't want to eat bases. Of course, we have some milder bases like tonic water, but again, tonic water has that kind of weird, bitter taste to it, I guess you would say. Bases also tend to feel slippery to the touch, so you probably know that with soap right away. But if you were to touch like ammonia or hydroxide, so like sodium hydroxide, all those kind of feel slippery. And of course, bases neutralize acids, and then they would change red litmus paper to blue. And of course, some common bases. And so we're pretty familiar with sodium hydroxide and potassium hydroxide. So both of these are used in soap production. And sodium hydroxide is also used in like petroleum processing or plastic manufacturing. Also in batteries. Sodium bicarbonate, so that's of course good old baking soda, could be an antacid and also just a source of CO2, so you know that you can decompose sodium bicarbonate, react it with an acid to get CO2 out. Then sodium carbonate, so So this is also a water softener, and also used in glass and soap manufacturing. And then of course, good old ammonia. It's either used as like in a cleaner, or it's of course used in fertilizer and explosive manufacturing, and also synthetic fibers. Questions? And so now we have this hydronium ion. And so all it's saying is that even though, like chemists, and myself included, we generally just write like H+, this is just saying that H+ by itself, naked, doesn't actually exist in solution. So essentially, and I don't really like the way this is written out. So kind of the proper way to do it, since you, again, you wouldn't have your proton hanging out there. So if we have water, and we'll get into this as we kind of continue on with this acid-base chapter, but water is very special in that it can auto-ionize, and so that basically means it can form ions with itself. And so what's going to happen is one equivalent of water can pluck off the hydrogen of another one. And so those electrons go back. So we make hydroxide here. And then we also form hydronium, this H3O+. And so again, this is just showing that when we say H+, we really mean hydronium. And again, you would never have like a naked H+ actually floating around in solution. And because if that were the case, it would just be immediately reacted with water or hydroxide. So again, it does not exist. So this is more, again, the proper mechanism of what actually happens. And so you can see, you know, it's often abbreviated like this, where you see just H+ plus H2O gives you hydronium. Sometimes you also just see like water splitting, like that, kind of colloquially written. And well, yes, that's effectively what happens. You know, it's not showing you kind of the full mechanism. So it's not just like spontaneously breaking apart, right? You have to have action at the electrons that are actually plucking it off and forming your two species. But again, you'll just often see H+ used, and just know when you see it, it really just means hydronium. They're used interchangeably. And so now we'll kind of look at these three definitions and talk about them. And so we'll start with our Arrhenius definition, and it's the simplest but also the most restrictive, so we'll see kind of what's wrong with it. And so kind of what we noticed is acids are substances that when dissolved in water produce a hydronium or H+ ion. So often, you know, we think about our simple HCl. So it can form, again, H+ ion, so that's not a very good mechanism. That's just kind of what we see. Same thing with like vinegar. I always forget the formula for vinegar. So 2 carbons. So H2C3. See, I forgot it again. Yeah. Oh. See, I would have a better shot of like drawing it out. I'm just going to draw out vinegar at this rate. It makes more sense. There we go. So vinegar, so again, our acidic proton, so we can say that it forms our acetate in solution, so H+ plus HC3 So those are, again, just our simplest definition. And then bases are substances that, when dissolved in water, produce hydroxide. So again, sodium hydroxide, potassium hydroxide, so all those disassociate. So let's look at our Arrhenius theory in depth. So again, we said that these were acids that produce H+ ions in solution. And so notice too, let's talk about equilibrium a little bit while we're looking at this. So HCl is considered a strong acid since it completely disassociates, so all of it goes all the way to the right and again forms our H+ or hydronium ions plus our anion, so chloride. And again, bases produce hydroxide, so sodium hydroxide, magnesium hydroxide, all of those are bases. Again, completely disassociated. And then, of course, in our Arrhenius acid-base reactions, again, they're kind of the simplest. And so in these neutralization reactions, we have our acid plus our base, always gives us water plus some salt. So, of course, in this case, it's HCl plus sodium hydroxide. So then they swap to make water and sodium chloride. And so now, let's look at, so what's wrong with our Arrhenius theory? Well, first of all, it doesn't explain why ammonia is basic, right? Because it obviously doesn't disassociate. So that's wrong. So that doesn't make any sense. And then it doesn't explain how sodium carbonate or sodium oxide, they dissolve in water to form basic solutions, even though they do not contain hydroxide ions. And so it also doesn't explain why CO2 dissolves in water to form acidic solutions, even though it has no H+ ions. And so now we can go back either up here. So this is what led us to the Bronsted-Lowry definition. And so now this is kind of our overview again. So now we're saying, well, acids, maybe they're any substance, donates a proton in water, so that means it's an acid. And then bases now, instead of forming hydroxide, we're defining them as substances that accept protons. So notice that it's a little more broad, right, than our Arrhenius definition, but then we'll see where it kind of fails. So let's go back to our in-depth explanation. And so this is kind of our overview for our Bronsted-Lowry definition. Again, we're just defining things by either H+ donors or H+ ion acceptors. So then we have some general, we have our acid, so this is just HA with our acid plus base, gives us now our conjugate base, so leaving us with A- plus HB, our conjugate acid. And so this means that Bronsted-Lowry acids are still H+ ion donors. And so often there's one hydrogen in the molecule that's easier to transfer, and that's, again, why we refer to that carboxylic acid. Probably misspelled carboxylic. And of course, our HCl still falls under this definition, so HCl. So instead, and I kind of like this mechanism better, because now we can better understand what's truly going on. And so what happens in solution? So we have our base, so there's our acid, and now it's going to, of course, pluck this off. So electrons go back to our chlorine, and so that gives us our conjugate base, our chloride, plus, and of course this forms our hydronium, H3O+. And so again, label this our conjugate base. So our new base that came from our acid, and now this is our conjugate acid that of course came from our base. And in this case, water was acting as a base. And we'll see this often, so water can act as an acid and a base. Again, why water is a very cool substance. And of course, HCl, our acid. And so now we can actually explain ammonia, though, from this definition. And so again, we said, well, with this Bronsted-Lowry definition, well, now a base has to be an H plus ion acceptor. And so let's see how this works in solution. So we have our base, and of course ammonia has those two, or our lone pair, or one lone pair here, plus water. And so then what's going to happen in solution? So now the nitrogen is going to attack our water here. So it's going to form ammonia. And so there's our definition. So it's a H plus ion acceptor. And then of course these electrons go back to our oxygen, forming hydroxide. So now we can label this. So this was our base, since it donated electrons or accepted a proton. Our water is acting as our acid now, since it's losing a proton. Now this gained a proton, so now we can say it's our conjugate acid. And of course our hydroxide is our conjugate base. And of course we can just write out our equilibrium as well and go backwards and forth. And let's actually write this out with our ammonia again. So we started off, so we're just kind of rewriting from before. So we had our acid plus our base, gave us ammonium plus hydroxide here. Now we can write the reverse reaction. So now hydroxide plus our ammonium. And so of course what can happen, and let's actually write out the mechanism this time. So we have our hydroxide hanging out in solution with ammonium. And so of course these electrons, so notice your action always starts at the electrons, and so now it can go and pluck one of these hydrogens back off. And so now we reform our water. So now this gives us H2O once again, and of course, ammonia. Yeah.
In this process, do you have to have a lone pair to make sure? Is that what so in front of the B above base, of the lone, yep. So yeah, are those electrons?
Yeah, so that's generally what it's saying. So the reason why it's accepting the H plus essentially is because it has electrons to grab it, yeah. So it has a lone pair and it's going to be grabbing it. Yeah, and that's really the key, is again, action starts at the electron. And I've seen textbooks and internet sources where it's like H plus attacking the base, and that is absolutely wrong. So again, you will see it, you'll see people do that, but that's not the mechanism. So action is always at the electron. So I'll just write that. So yes, those electrons are grabbing that proton. And so that kind of leads us into our last definition. So we'll go back to those conjugate base pairs. But we don't really talk in depth about this last one. And so the last one is the Lewis definition. And so this is really the best definition. And so it's again based on now electron donors and acceptors. So acids are any substance that can accept or needs an electron pair. And bases are substances that donate an electron pair. And so let's see one of those examples. And so one of these acids, so BF3 would be acidic. And so we can tell that it's acidic since it would want an electron pair. So boron, we mentioned, is kind of one of those odd ones. And it's currently electron deficient, right? It only has 6 total electrons, but since boron only has 3 valence electrons, there's not much it can do at this point in time. But then we can make what's called a Lewis base pair. And so if we pair it with any sort of like nitrogen species, so we'll just look at ammonia to keep it simple. And so, right, ammonia is going to be our base again. And so now we can see that they would make this acid-base pair. So nitrogen's going to donate both its electrons to boron. And so it would make a bond like this. And I drew it with an arrow only to show that nitrogen is donating all the electrons. So if I just drew like a normal line, that would suggest what's called a normal bond, where each one is contributing 1 electron. But in this case, this is called a dative bond, where nitrogen donates both electrons. And so there's also like a whole vein of research devoted to these Lewis acid-base pairs. And sometimes they're called like frustrated Lewis acid-base pairs, where you try to get these substances really close, but like not quite, and then try to get them to do cool stuff because they want to kind of go back and forth. And I think I've mentioned this before, but again, boron is a hot area of research because it does all this cool stuff. Making 3 bonds, making 4 bonds, and then being able to go kind of back and forth between the 4 and the 3, which is useful for catalytic cycles and all that good sort of thing. And so now let's go back to this conjugate acid-base pairs. And so what you're probably noticing is our original base then becomes our conjugate acid, and then it becomes our acid if we start looking at the reverse reaction, just like we saw up here. So we had our base, it became our acid, so now it's our acid, and then we convert it back to the base. So you can probably already seeing, right, the equilibrium. We're kind of teasing that too. And then, of course, our original acid becomes our conjugate base, and then now it's our base in the reverse process. So then we want to be able to identify these conjugate acid-base pairs. And so they should only differ by a proton. And so in this case, if we are starting with a base, then we should be adding a proton to make our acid. So there's our base, there's our acid. Or we could, of course, remove a hydrogen to get our acid-base pair. So water is our acid, remove a hydrogen, and get our conjugate base. And so, of course, again, in this reaction, we had our base with ammonia, added a proton to make our conjugate acid. Same thing, acid, removed our proton, made a conjugate base. All right, so take a moment for this example for both A and B. So identify the acid, the base, the conjugate acid, and the conjugate base. So looking at A here, what do we think our sulfuric acid is? Yeah. So it's acting as our acid here. So we can see, right, looks like it's losing a proton. And so if this is our acid, what's our HSO4 species now? So conjugate base. And so this is our acid. What does this make? Water? Excellent. Our base. And so we can double check. Oh, yep. So it looks like it donated some electrons to grab that proton there. And then, of course, what's H3O plus now? Or hydronium? So conjugate acid. So that looks good. Any questions about that one? And so let me at least write this one while you finish up your thoughts. So now looking at this one, so what's this bicarbonate species? Is it an acid, a base? So it's our base this time. And so if it's our base, what's water acting as? Acid. And so now we can kind of see how that might have gone down. We have to write our bicarbonate species, so H. So now we can write out our mechanism so we can understand what we're starting with. And so we can see, so this oxygen plucked off one of our hydrogens here from our water. So good, so we can again clearly see how this is donating our proton. And then so this formed our carbonic acid. So what is this called now? So conjugate acid, perfect. And of course that leaves us with hydroxide, which we know hydroxide's a base, we can call it our conjugate base. Questions about that one? Excellent. And then, sorry, let me erase those old notes. And so what I was writing down here is don't get tricked. So often on your exams or questions, you see stuff like identify the conjugate acid-base pair or something like that. And so all I mean by that is, for example, hydronium and water, right? This would be an acid-base pair. But then sometimes you'll see written out like something like this. And would this be an acid-base pair? So what's the problem with it? And we can even think back. So think back, what was it trying to show us right here? Right, we're either adding one proton or removing a proton. So what's the issue with this species? So how many protons do they differ by? So I see, yeah, 2. So that's inappropriate, right? They differ by 2 protons. So it's not a base pair because you need water in the middle. So not acid-base pair. So they have a 2 hydrogen difference. I think that's the easiest way to kind of identify and explain it. So this would not be a pair, but this is a pair. And then we can write, so H2O and hydroxide, well, that's an acid-base pair, so that works. And so same thing with like the carbonate, so you have H2CO3 and HCO3. So, right, that's an acid-base pair. And then this bicarbonate can go on to lose another hydrogen just to make carbonate. Oops. Sorry. 2 minus. And so that's an acid-base pair, right? But carbonic acid and carbonate, that's too many now, so this is not an acid-base pair. Yeah.
So your HCO3 to CO3, 2 negative, we would know that that's an acid-base pair because of the electron count, the charge on it?
The charge and the fact that you've lost the proton. So that's where the charge went with the proton. So yeah, you're just kind of looking, well, they're a proton different. And so, right, if we added the proton back in, that would get us back to HCO3. And I could write that out if you, it might make more sense with the mechanism. So we're here. And so now we'll just take our generic water for a second. And so if it deprotonates it, right, that sends the electrons back there. So that's how you get carbonate now with our 2 negative charge. And then, of course, making hydronium. So there's your charge balancing out. And so same holds true, so you could go crazy. So there's also phosphoric acid. And of course, you lose 1 proton. So there's 1 conjugate acid-base pair. And then you can just continue going on. So you lose another to form your next step conjugate base pair. And then your last one. So now you get your phosphate, 3 minus that you're familiar with. And then obviously, right, you can't mix and match, so phosphoric acid and phosphate would not be a conjugate base pair, so those are 3, and vice versa. So like this one and this one are also not appropriate, still too far. And I'll just write one of those examples out. And again, the easiest explanation I can think of is they're more than 1 hydrogen apart. So now we have 3 versus 1. So 2 hydrogens apart, so not an acid-base pair. So that's kind of the key, because you'll see that a lot. All right, let's keep going. And so now, this brings us back to our equilibrium. So again, the true definition of a strong acid and a weak acid has nothing to do with how dangerous it is, but rather how much it ionizes. And so like I kind of mentioned before, a strong acid is a strong electrolyte, meaning it completely disassociates. And again, I'll rewrite that for HCl. My simplified mechanism. But again, all of it is converted all the way to the right. Meanwhile, with a weak acid, so if we write our vinegar, we have an equilibrium established. And so again, the reason why vinegar is a weak acid is because it can go back and forth. And so we make our acetate anion. And I'm just doing our simplification, so plus H plus. But then this can reform acetic acid in solution. And so we can write then the opposite or backwards reaction. And so this gives us acetic acid back. So same thing, a strong base is a strong electrolyte, completely disassociates. So sodium hydroxide would completely disassociate versus, so ammonia, so that's a weak base. So then again, we have our equilibrium. And then again, the key point being that our ammonium can react and reform our ammonia. And I don't, maybe it was this class, there was like some lab that we were doing sometime where we were like trying to add ammonia, unless this wasn't this class. But basically what I'm trying to say is if you ever see like ammonium hydroxide in a lab and it's asking for ammonia, it's the same thing. Because you notice in solution, right, your ammonium hydroxide will make ammonia. Other questions? And so now this is just kind of general trends in acidity. And so the stronger an acid is at donating a proton, then the weaker the conjugate base is at accepting a proton. Well, let's break that down, what it's truly saying, because it's going back to our equilibrium, but it's kind of important. So all we're saying is, so let's say we have HCl. And again, we said, well, it disassociated fully. So, okay, the stronger the acid is at donating the proton, then that means the weaker the conjugate base is. So this means that chlorine is essentially super weak that it can't do that. And so that's all that's saying, is we have a really strong acid of HCl, and so chlorine, right, cannot reform. And this is truly the reaction that we're thinking of is chloride plus H2O. Does it make HCl? And the answer is, in this case, it is so strong that no. But then when we're talking about other cases like acetic acid, let's take it back to acetic acid. So that does have equilibrium. And so that means that this conjugate base can accept our proton. So this isn't as strong, right? So it's still donating, but it's not as strong as our HCl. And now we can say this acetate is going to hang out with water here, but then it's going to pluck off. So this negative charge will attack our hydrogen and, of course, reform our acetic acid. So that can happen. Again, that's why we use the equilibrium arrows in this expression and our single-headed arrow for these strong acids. And so what we also find is the higher the oxidation number, the stronger our oxy acid. So aka the more oxygens on there, the stronger the acid. And that's usually because our oxygens can help stabilize our negative charge. So then that means it can lose protons just fine. And then we also have our cation is a stronger acid than our neutral molecule. And this will become relevant when we talk about like salts. But basically only cations can be acids, but of course not all cations are acids. And then neutral molecules are stronger acids than anions. And anions tend to be bases. So put anions are bases. So hence why a neutral molecule would be a stronger acid than an anion. And in retrospect, I should have printed out this chart for you. I can bring it for Tuesday, but this is also helpful. So up at the top here, you have your strong acids, so perchloric, sulfuric, hydrogen iodide, hydrogen bromide, hydrogen chloride, and nitric acid. And notice, right, they have here undergo complete acid ionization in water. So that's telling us the equilibrium lies all the way to the right, and none of these can reform the acid in solution. So for example, let's just look at nitrate. Go over one of these. So again, we're saying that it fully ionizes. And so that means our nitrate is not going to react with water. It's not going to do anything, right? The equilibrium can't go back, so it can't reform nitric acid. Now, once we get below that, now they can have some sort of equilibrium. So we have our hydronium, and this is, notice, increasing acid strength. So hydronium's under nitric there. Then it kind of has its base pair across, so that is helpful. And so you can just kind of look at this. So your hydrogen sulfate loses one to have your sulfate. Notice increasing base strength goes down towards the bottom here. So there's HF. And so now in this case, right, like fluoride can reform in solution. And so this can be dangerous, for example, and we'll talk about this with our salts more. But if we look at HF, so HF, we said it can reform. And so let's just say you're doing some reaction and you form like a fluoride as a byproduct. This is dangerous because you have fluoride plus water. Well, we said that there's equilibrium here. So this fluoride can go ahead and pluck off one of those H's, reforming HF and making hydroxide. But now, right, this HF is bad. And so you don't want HF, you don't want to form HF in a reaction. So if you were doing this as a chemist, you would want to be like neutralizing that reaction somehow, because HF is, again, not good. You don't want to be mixing it with other acids. You don't want to be like generating it as part of your reaction and not realizing it. And of course, I think I mentioned the dangers of HF before, where if you get like a drop on you, it'll go into your body, absorb or dissolve the calcium in your bones. The calcium then will be free ions running around in your bloodstream until it recalcifies somewhere, and you don't know where that would be. So, and you have, if you are working with HF, that's why you have some sort of calcium compound. So antidote, so if you do get it on you, put that calcium compound on you so that it reacts with the calcium as opposed to the calcium in your bones. But that's why it's super important to be kind of conscious of that. And so even though you weren't working with HF, if you have fluoride ions in solution, you have the potential to make HF. So then you want to neutralize that and make sure you're not making HF. So safety tip. What else? So you can, again, just kind of read this for yourself, seeing our acid-base pairs here and the strength. So again, decreasing acid strength. So now we're at ammonium and ammonia, increasing base strength down to here. Yeah.
So for the strong acids, you said the equilibrium lies all the way to the right. So for the weak bases, the strong bases, would the equilibrium lie all the way to the left?
All right. Well, to the right, because we still write it like.
Okay, still. So even though it's a, okay. If my question makes sense, I'm just trying to make sense.
Yeah, but it's like the same sort of concept. So basically, right, your sodium hydroxide, oh, I wrote that all wrong, but. So our sodium hydroxide, yeah, lies all the way to the right though still. And so then it's not going to reform or anything in solution. And so I feel like here we're just teasing the math for spring. And so now we can have our equilibrium. And so this is, again, our strong acid. So this means our Ka would be much greater than 1. And let's write out, I don't think we wrote out our generic expression for Ka. So then we have, right, our Ha, so our acid, disassociates to give us our H plus our conjugate base. So then we can write our Ka, of course, good old products, over reactants, just like we've seen before. And so now, putting this all in context, we're just kind of saying the same thing. So strong acid, their Ka is greater than 1, aka, right, all these products are going to be much greater, aka they're fully disassociated, just like we've been saying with the HCl and our other strong acids. So that makes sense. Should hopefully tie back into the equilibrium chapter we've just been talking about. And just like before, our brackets all designate molarity. And so that means for weak acids, their Ka is going to be less than 1. So weak acids only donate a small fraction of their hydrogen atoms. And so the weak acid, so our concentration would not equal our concentration of H plus ions in solution, and we'll kind of get into the math of that. And so examples of common weak acids, so we've mentioned vinegar a lot, carbonic acid, formic acid, and there's tons of organic acids as well. And so now again we have our equilibrium constant. Notice, right, water doesn't count. That's just a liquid. It's what the medium is in, so we can ignore that in our expression. So that's, again, how we got to this point. And so now we're kind of teasing it. So if we have our Ka of, I think this is chlorous acid, is 1.1 times 10 to the negative 2. And the Ka of HCN is, or hydrogen cyanide, is 4.9 times 10 to the negative 10. So notice, right, this is a much smaller number. So that means that this acid is stronger. So again, just based off of our equilibrium constant. And so the position of equilibrium depends on the strength of attraction between the base form and the H plus form. And so again, now we have our acid ionization constant. So just writing out our equilibrium expression and just formally calling it Ka. And so again, the larger value of Ka, the stronger the acid. And so now let's look at this table and some key relationships. And so we have chlorous acid, and so notice our pKa. Well, let's first write out our relationship. So what the heck is pKa? So pKa is equal to the negative log, and this is base 10 log of our Ka. And so the smaller the pKa, the stronger the acid. So notice that. So as our pKa gets larger, our acid gets weaker. And you can tell that with our equilibrium constant. So notice phenol is a pretty weak acid, so this is an organic compound. And so there's acetic acid. And so let's just plug one of these values in. Let's do benzoic acid. So benzoic acid, and again, you could be given the Ka, the pKa, So usually organic chemists start talking about like pKa's just colloquially, but you'd want to be able to get that back. And so again, I'll just rewrite it to pKa equals the negative log of our Ka. Forgot to pull up the calculator. And so let's just plug in. So if I do my negative log, 6.5 times 10 to the negative fifth, I get back 4.19. And if you ask Google, I would expect like minor discrepancies in these numbers as well, so just be aware of that. And then if we want to go from pKa back to log, right, we just take 10 to the power of our negative pKa. I think I used the wrong negative sign, hang on. And notice back we get out the Ka, so 6.5 times 10 to the fifth. And then again, we have our ionization reactions here, so this corresponds to our Ka expressions. And so we've kind of seen this. So again, water is amphoteric, so that means it can be an acid or a base, and we've seen that already. And so the other thing that water can do is, again, that autoionization process that we kind of looked at, with the oversimplified view just being H2O splits, but really we saw that mechanism, again, where water grabs the hydrogen off of another water. And so what they kind of found when they were like researching this and trying to first figure out pH and all this good stuff is they determined that neutral water has equal concentrations of our hydronium and hydroxide. And so these are some key points. So of course we know aqueous solutions contain both hydronium and hydroxide. But the key thing that they found was neutral water had, again, equal concentrations that were equal to 1 times 10 to the negative 7 molarity, and that's at 25 degrees Celsius. So there'd be small deviations if you deviate away from 25 degrees Celsius. For our purposes, we always just assume that. And so now this kind of starts explaining how we get our pH scale and why it goes from 0 to 14. And so our product of hydronium hydroxide concentrations is always the same. So that's going to be 1 times 10 to the negative 14. And so that means this is our Kw. And again, that holds true at 25 degrees Celsius, so you would have deviations away from that. And so that means if we know hydronium, we can figure out the hydroxide concentration, or vice versa. And of course, we'll see they're inversely proportional. So if one increases, then the other must decrease. So neutral solutions have, of course, equal hydronium and hydroxide. If something is acidic, that would mean it has more hydronium in solution than hydroxide. And of course, if it's basic, then it has more hydroxide than hydronium. So now take a minute or so and figure out whether these solutions are acidic, basic, or neutral. And you can calculate the hydroxide concentration.
Go back to your math on the benzoic acid when you went from the pKa back to the Ka. So you just put the pKa number to the power.
So what do we get for A here? Yeah, what do we think? Acidic, basic?
Acidic.
So acidic, so it was greater than 10 to the negative 7. And then what was the hydroxide concentration? Calculate that. So we just have to divide. It should be something like the order of 10 to the negative 9th, I'm assuming. Or the 10th, so somewhere around there. So you can always double check your mental math. So 1.3 times 10 to the negative 10 equals hydroxide. What about B? Acidic, basic, neutral? So basic, and so now it has less than 10 to the negative 7. And then do we calculate our hydroxide concentration? What do we get? I'm assuming something to like the negative 4 or 5. Oh, 6. Off on my mental math. So 6.6 times 10 to the negative 6. And then what about C? Acidic, basic, neutral? Yeah.
That would be neutral, and it would be the same concentration of OH.
So that looks good. So again, exactly neutral. So we could calculate it. B was the same. Perfect. All right. And so this is kind of the harder way to do it. The easier way is to plug it into this expression. So it should look pretty similar to the pKa one, except now we have pH is the negative log of our hydronium concentration. And so anything with a pH less than 7 is acidic, greater than 7 is basic, and pH equals 7 is neutral. And so just like the pKa, if we know the H plus concentration or the pH, we can go back and forth. So if you were given just the pH, you could do 10 to the power of the negative pH to give you your molarity concentration. And so this is just kind of some context so you can tell what's what. So your stomach acid is super acidic. So that's why, you know, people with like who have bulimia, they tend to start like rotting their teeth because it's just so acidic, so you don't want to throw up. Or if you do throw up, right, that's why you want to rinse your mouth out so that acid doesn't just bathe over your teeth. And so limes and lemons, so those also have a pretty low pH. Soft drinks are also pretty low pH. And then have you guys had those substances that like block your sour receptors so you eat a bunch of sour stuff? And then so those are, I mean, they're tons of fun, but you have to be careful because you don't want to, you know, again, overstrip your mouth or anything. Usually people do them in college. I feel when they're like way too drunk and inebriated, then you wake up the next morning and your mouth is super sore because you were eating a bunch of sour stuff and you didn't have any receptors to tell you stop. So that's my only cautionary tale for those sorts of things. And then so plums and wine is also pretty acidic. So again, if you're paranoid about your teeth, you can worry about wines kind of wearing down your enamel. And then so fruits, so now it's starting to go more neutral. So beer, still a little acidic. So rainwater tends to be around like 5.6 or so, kind of depending. I would love to know the pH of the water around the East Palestine in Ohio, see the effects or not. I think that would be like the bigger, like local immediate effects is just all that HCl, and then it's probably going to be rained back down. And of course, acid rain can be pretty destructive towards trees and roots and kill fish and all those things. So I'm sure we'll be hearing about the studies. And then human blood. So notice that's kept at a pretty tight pH. And so, right, your blood is a buffer. You have all these wonderful reactions going on, so it has to be pretty precise there. So egg whites are a little basic. Milk of magnesia, so that's like 10. So I don't know if anyone's taken that for like an upset stomach. And then ammonia is pretty basic. And then sodium hydroxide, of course, would be 14. So again, here's our pH scale. That's why we go from 0 to 14 based off of our KW constant. So let's try this one. So see if you can tell me what the pH is and if it's acidic, basic, or neutral. All right, what do we get? So what's the pH for A? It sounds right. I'm just guessing off of this is -4, so I'm assuming it's around 3 or 4. And then what do we get for this one? So I think 1.886. So was that when you plug this into the negative log? Except this is hydroxide concentration. So actually what you calculated was the P at OH, which we're about to get to. And so what you could have done, since we don't know this yet, is you could have found, using our KW, the hydronium concentration. So 1 times 10 to the negative 14 is equal to this times hydronium. So this is kind of like the long way. So then that gives us like 7.69 times 10 to the negative 13 for our hydronium concentration. And so from there we could have plugged in our pH, so negative 1 × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10 Or what you could notice, and we're about to get there in our notes, is if we found the pOH here, so we can say pH equals 12.11 with this method, or if we solve for the pOH, we're about to learn that pH plus pOH equals 14, which is super useful. And so we could just take 14 minus our 1.89. And that also gives us 12.11. So either way, we should get 12.99 for that one. So let's look at pOH. And so again, this formula looks just like our pH and pKa, Ka expressions. So now we have our pOH is equal to our negative log of hydroxide concentrations. We can go the other way too. So we're given the pOH. We can take 10 to the power of the negative pOH, give us a concentration back. And again, go back and forth. And so, of course, other key points is the pOH scale is the exact opposite of our pH. So pH 0 is the most acidic, with 14 the most basic. pOH, now 14, is the most acidic, and 0 would be our most basic. And so that leads us to this relationship. So I would highlight that, write it. So that's super key. And that's what's really nice about this math, is you can kind of go back and forth, whatever feels better to you, is you can use your molarity concentrations and our KW relationship, or, so you can see the derivation there, but essentially you could use either one of these relationships, and you can solve for all of these and kind of double check yourself all the way around. Now we have buffer solutions. And so buffer solutions are solutions that resist changes in a pH when an acid or base is added. And so this happens by the buffer either neutralizing the acid or base that is added to the buffer solution. And so the key way to make a buffer is it has to have either a weak acid and its conjugate base, or a weak base and its conjugate acid. So notice, right, it has to either be a weak acid, weak base. You can't make a buffer with HCl since that doesn't have an equilibrium. And so again, your blood is a good example of a buffer system in nature. And so again, if we need our acid and a conjugate base, if we're trying to make a buffer solution, let's say we pick acetic acid, then we know its conjugate base is acetate. And so we can pick any appropriate salt then. So in this case, they picked sodium acetate, but there's no reason why it couldn't have been lithium acetate, potassium acetate, right? It doesn't matter. The key thing that we need is that acetate. Blah, blah, blah. And so it kind of works. So if we have, in this case, if we add a base to our buffer solution, then it's going to react with our acid to neutralize it. If we add an acid, then the acid will react with our conjugate base, or react with our sodium acetate species to reform our acetic acid, and then of course salt. And so again, that's the key point here, is either we're making our conjugate base back in solution, and then we have, again, equilibrium, so we can reestablish that equilibrium of acid-base. So, right, even if we add a base, so we form this, but then it will potentially, right, reform our acid and again kind of negate the increase. So again, same thing with this scenario. Acetic or acetate reacts with our acid, reforming, right, our acid there. And so again, we can have our equilibrium. And if we need to make more conjugate base, it will, and kind of again mitigate the effects of that pH change. So we're kind of running out of time, which is unfortunate. So let's leave off with this Henderson-Hasselbalch equation. And so this is probably the easiest way to calculate your pH of a buffer solution. And so notice, right, your pH is your pKa plus the log, and notice it's base over acid in this case. So if we were looking at our acetic acid here, right, this would be on bottom. So this is equal to HA of acid, and then acetate would be on top. I should rewrite that. So plus log, so in this case, acetate concentration, so whatever they said, over your acid concentration. And you may see this in reverse. So pH is also equal to the pKa minus the log of acid over base. So if you see this, know that it's the same thing. It's just when you do the minus sign here, then it's acid over base. Me personally, I like this formula better. Again, they give you the same answer, but just be aware that that's why you'll see one form with the plus sign and one sign with a negative, and don't get confused. All right, I think we have to stop there for now. So I'll probably finish up on Tuesday before our review, just kind of going over this acidic, basic, neutral stuff, because I don't want to not talk about it. But we are out of time. All right, so let's take our 10-minute break, and we'll come back and do our Chapter 19 quiz. Don't forget to grab a Chapter 20 quiz and a homework so you can do those. And then I'm going to go ahead and stop the stream here.